All right, so I'm going to talk about obfuscation of probabilistic circuit. This is joint work with Ron Canati, Stefano Tesaro, and Vinod Vankutanathan. Seems unfair if I pronounce everyone's last name.
Who was the last one? Sorry.
It's recorded, by the way, and you can never erase it. All right, let's start. All right. The goal of obfuscation in general is just to compile a program in a clear and into an unintelligible one while preserving functionality, which is a very good goal. And surrounding what does unintelligible mean, there are actually many different notions, as we can see, from the strongest of virtual black box to the weakest indistinguishability obfuscation, and in between there's VBP and then DIO, and OnCam just talk about DIO for only public coin DIO. And it seems that right now still that IO is the right notion to work with because it's weak, there's no impossibility, we have candidate for it, there's active research on it, and yet it's extremely powerful. Okay? But nevertheless, I'm going to add one more notion to this picture because it seems so far all the obfuscation consider only deterministic programs. Okay? And why does it have to be like this? And already this need, the definitions of those obfuscations are tailored for deterministic program, as you can see already in the correctness requirement. That we actually require that the obfuscated program should preserve the functionality, meaning that for every input, they will output the same output as the original program. If you want to say this, it means the original program is deterministic. But why does it have to be? There are probabilistic programs, and we know in general they are more powerful, more general, and in particular we have lots of cryptographic algorithms which inherently use random coins. And as we see in many applications of obfuscation, that we would actually like to obfuscate as a part of whatever application you're dealing with, some sort of cryptographic algorithm into it. Well, seems like a very natural notion under our nose, so why didn't people look at it earlier? Maybe the answer is that why bother? I mean, what's so special about probabilistic program? They're just programmed with some additional randomness, and I can view the randomness as extra input. If I view it that way, it becomes deterministic. And I can just use whatever IO that we have been using. So to see why should we bother or not, whether it deserves a paper or not, we're going to look at some motivating examples, right? So here are two examples. One is that for whatever reason, I would like to publish an obfuscated program that does oblivious sampling. That it's, you can view it as I push a button, it gives me a randomly sampled DDH tuple. Okay? Another motivating example could be I want to do oblivious re-encryption. I want to publish a program that, given any ciphertext, this program is going to kind of decrypt it and re-encrypt it using fresh randomness. Okay? Seems reasonable things to, yeah?
If I did like the trick from today's vector resettable stuff and put a PRF inside with a key and applied the key to the input and use that as a randomness, that would also be okay for these applications. Right,
that's exactly going to be our construction. Thank you. The construction is extremely simple. The question is, what kind of property does it give us? Yeah?
So I thought in this left example, the point is there is no input. You push the button.
Yeah, but I can't really push a button. It's a program, and this obfuscation, you will see that it's actually going to be deterministic. So the way to say that I'm going to get many samples out of it is to say that I'm going to input 1, it give me 1. Input 2, it give me another 1. Yeah. So it's equivalent to saying I'm pushing a button. All right. So in both of these situations, I want two things for my random coin. One is the coin should be hidden, right? If it's not hidden, then what's the use of getting those outputs from them? The other is that I want the coins to be unbiased. On the other hand, if I treat the coins just as a part of the input, the evaluator can arbitrarily bias the distribution of the coin, then it's again useless. Okay. So this tells me that maybe probabilistic program, there is something that's non-trivial going on. Okay, so this work we're going to study indistinguishability of obfuscation for probabilistic programs. We're going to shorthand it as PIO. And it turns out, as we will see, that defining it is not straightforward. And there are a couple of different variants you can go about it. And in this talk, I'm going to mainly focus on one variant, which we call XPIO in the paper. We can do two things with it. The first is that we can construct, so PIO actually exists. So if I have sub-exponential IO, then I can get PIO. I'm hiding some other assumption of one-way function here. Another thing is that I want to show you that PIO as a notion is useful. That we can actually use PIO to kind of transform any re-randomizable public key encryption into a fully homomorphic encryption. And the neat thing about doing this is that I don't need to rely on any circularity assumption. Okay? There's no need for circular security. And next, I'm going to first try to tell you about the intuition of what is PIO, and then a little bit about the proof high level of those two theorems.
Maybe you'll talk about it. It's just I remember in the old days, like a year ago, constructing FHE from I/O was open. So using your things, this is the first construction of a FHE from I/O? Or?
Yes. Yes.
I/O plus extra stuff.
Yeah, from I/O plus extra stuff.
Oh, I see. So randomizable.
Right.
Do you need public key? You can just do, for example.
Do I need a public key?
Yeah, public key encryption, or you can get public key encryption from symmetric.
Yes. Yes, right. So you can use.
Yeah,
No, the thing is that we want randomizability. Yeah.
You can build a randomizable PK.
So this is sort of draw a connection between I/O and FHE, that you can view it as sub-exponential I/O implies FHE, except that we need a little bit more, which is the re-randomizability part, which you will see why it comes into play.
You can't build randomizable PKE just from secret key encryption and PIO.
I tried, it didn't work out for me. But maybe someone else can. All right, so what do we want when we try to obfuscate a probabilistic program? Okay. First of all, I want to turn, so the paradigm now becomes I want to turn a probabilistic program into an unintelligible and deterministic one. Okay. But I still want to say it preserves functionality. So what does that mean? I cannot say that this deterministic program output the same thing because there isn't any single thing. So to say preserving functionality, I will require the output distribution to be indistinguishable. Okay? And in particular, on the left-hand side, the distribution is going to be taken over the randomness of the probabilistic program. On the right-hand side, since it's a deterministic program, there isn't really any randomness. So the randomness is actually the randomness used by the obfuscator at the time of producing this obfuscated program.
And it's enough to require it only for a single X without the correct X?
Of course not. As you see, it's not enough because I'm only considering one single input. What about the joint distribution of outputs from different inputs? And as you can see that since the obfuscated program is deterministic, it's easy to distinguish if one gets the output for the same input twice. Okay? So the strength and the correctness is that you should not be able to tell apart, and the adversary cannot tell apart whether you're getting output from P or you're getting output from the obfuscated program, provided that he does not ask the same input twice. So this is as much as we can achieve with correctness. So the more interesting thing is, of course, security. What can I get? Well, plain I/O tells me that if two deterministic programs are functionally equivalent, meaning that they agree on every input, then the obfuscation should be indistinguishable. Okay? Now when we move to probabilistic programs, functional equivalence doesn't exist. Intuitively, I would want to say that the program should be functionally indistinguishable. Okay? Think about that. I want to say program P is producing encryption of 0, and program Q is producing encryption of 1. Okay? If the adversary have no secret key, then I want the obfuscated program to be indistinguishable. Okay? Well, the intuition is it's a very natural line of thought, except that the function indistinguishability turns out to be not so easy to define. And you can define it in many different ways, and every notion of functional indistinguishability will give you a corresponding notion of PIO. The question is which makes sense, and whether for a corresponding one does it exist or not. So we can try to start, again, following the natural line of thought. Let's start with defining one notion. Okay? So here I'm going to consider a sampler, which is going to sample a pair of program P and Q and some auxiliary information. And I will call this sampler dynamically indistinguishable if the following two games are indistinguishable. Here the adversary is given the tuple sampled from the distribution in both words, and he can dynamically choose the input. And for that input, he gets to see the output of the program, either from P or from Q. Okay? And the randomness is generated at random in both games. So, well, it seems reasonable. We require that the view of the adversary should be indistinguishable. And this indistinguishability will give me a notion of PIO, which is for any such pair of programs, the obfuscation should be indistinguishable. Seems very natural, but it turns out that if you just look carefully, that when I restrict the P and Q to be deterministic, this notion actually exactly collapses down to different input I/O. So therefore, it suffers from some implausibility result. This seems to be a little bit stronger than what we want, because what we want is something that is more closer to I/O rather than DIO. So what that means that I actually need to consider stronger indistinguishability. By making the indistinguishability stronger, it makes the premise stronger, and therefore make the PIO notion actually weaker.
So you're saying intuitively because, the attacker explicitly provides input, so somehow if you can distinguish, you can find which input is...
Exactly.
Public coin variant will also be the same then?
Public variant, I guess, we're corresponding to that this auxiliary information is going to contain randomness for sampling P and Q. Is that right?
Is it meaningful then? Because there is supposedly no implausibility results for public coin, so would it be a useful notion?
It's a reasonable notion, but we didn't study the power of it. Yeah.
Without putting the encryptions of 1 and encryptions of 0, for instance. Because it will reveal what you encrypted, right?
Yeah. Implication the other way is easy to see it might not be true. PIO.
Yeah, but in terms of applications.
What do you mean? PIO to what?
So this implies PIO if you consider.
Yeah, so PIO is even more general than DIO. This notion of PIO is more general than DIO because it considers randomized programs. Okay. All right, so how can I strengthen this indistinguishability? I'm going to make two simple modifications to the previous game. The first modification is that instead of letting the adversary choose the input dynamically, I ask him to choose it statically. Okay? Turns out that if I do this, I actually make the indistinguishability weaker. Okay, so I could also consider a PIO notion corresponding to this indistinguishability notion. But that is going to become impossible. So, to actually strengthening it, I will require that the view of the adversary in those two games to be extremely indistinguishable. Okay, the distinguishing gap is tiny. How tiny? It's negligible over x, where x is the number of inputs. Okay? In many programs, you can imagine the number of inputs is going to be something exponential. So it means that these two games are inverse exponentially indistinguishable.
What is
Computational or statistical? Sorry.
Computationally, yeah.
negligible over divided by x?
Something that
Multiplied by x, it remains negligible.
All right, so
What did you say? So before you introduced this very strong indistinguishability, you said something was impossible. What was it?
right. So if I consider for any distribution that are computationally indistinguishable, and I require that the obfuscation for such distribution to be indistinguishable, that also gives me a notion of PIO, right? And that notion is impossible.
Why is it impossible to achieve? For the same reason as implausibility for differing input, or is this some?
I can tell you about the proof, which isn't hard, but I just don't have it on top of my mind. Yeah.
You can't say whether it's like the BBB type impossibility or the DIO type impossibility.
BBB type is unconditionally impossible. Yeah, there exist actually distributions that satisfy this indistinguishability that you can't hope their PIO are indistinguishable. Yeah, no matter how you fuscate. All right, so given this very, very, very strong indistinguishability, let's leave it aside how reasonable it is. I can record that for such distribution, obfuscation are indistinguishable. And this gives me a very, very, very weak PIO notion. And it seems really arbitrary, right? People are probably all like gazing at it, what is negligible over X indistinguishability. Turns out this gap is tight. In fact, if you relax this gap to say that the two words are, the gap of the two words is less than 1 over, more than 1 over X, then this notion becomes impossible. Okay? So essentially, this is necessary. This is the only thing we can achieve.
One question, I mean, so the alternative, incomparable option would require statistical indistinguishability with negligible. Is this notion useless? Like you can
statistically close. It's not. You cannot
use it.
It's not useful in some sense.
Sometimes you can like unconditionally argue statistical distance.
You can, but usually I feel in that case you can probably use IO instead.
Right, I see.
Because why do we want to consider those computational indistinguishabilities? We want to use crypto inside. Right. If you have some crypto that is statistically secure, then with some effort you can just use IO basically.
Okay. X is the number of inputs, right?
X is the number of inputs.
It can be exponential anyway for any of the functionalities.
Yes, but the adversary is PPT. So you can.
Over 2 to the k. Why isn't that statistical?
Why isn't that statistical? Well, if I have sub-exponential encryption, for example, by making the security parameter large enough, I will be able to have a computational distinguishing gap smaller than the number of inputs.
In other words,
that's computational.
The number of random coins can be much, much bigger than X. It can be much bigger than log X. Yeah.
So in particular, for example, if I was using it only for encryption, bit encryption, then X is just 2, right?
Right. The input to your obfuscated program, right. Okay, so it's great that people are asking questions, but I'm worried about my time. Because if some of you are at TCC can remember that I was, there were a second half of my talk that wasn't covered in the talk under the careful watch of Shai. So I was hoping that I would be able to go over that. All right, so as you can see a little bit already that this notion how to define PIO is intricately related with which notion of indistinguishability you consider. And there are many different notions you can consider. So in the paper, we actually name a few different variants, and we study the relationship between them. And I'm going to only focus on XPIO, and I will show you next that this is one of the weakest variants you could consider, and this is implied by sub-exponential IO. And the construction proof is extremely simple. All right, so what is the construction? We're given with a sub-exponential I/O, and we want to obfuscate probabilistic program, P. What else can I do? Well, I'm going to first de-randomize this probabilistic program using a pseudo-random function, a puncturable one, and then I'm going to obfuscate this de-randomized program. Okay, so just as anybody would do it. And let's see whether this is actually secure. Okay. As a thought experiment, let's assume that the P and the Q have only one input. And since they only have one input, I require the output distribution to be indistinguishable. Okay. And to show that now this construction of PIO is actually going to be indistinguishable, I just need to look at the IO of their de-randomized version. Okay. And the proof is really one-liner. Okay. Since the programs have only one input, well, I might well just hardwire the output, since there's only one input, right? So I hardwire the output, which looks like this. What they are, they're essentially the output of the original program using some pseudo-random coins. And since the PRFs are indistinguishable, I might well just hardwire a randomly sampled output. Right? And now, because the outputs are indistinguishable, we have a bridge. Therefore, if there were only one input, in fact, even I/O suffices for this construction.
And you don't need puncturable PRF even for this.
You do.
We don't need puncturable for this single input one. Yeah, but when you go to multiple inputs, well, what do? We're going to start to look at an exponential number of hybrids, where the number of hybrids is the same as the number of inputs. And as you can imagine that we're going to start from one end, which is obfuscation of P, to another end, which is obfuscation of Q, and we're going to kind of gradually morph those programs one input at a time. So if I look at the two neighboring hybrids, they're going to divide which program to use to evaluate the input in a kind of just one step at a time. So in neighboring hybrids, the two programs obfuscated actually only differ on one input. Okay? In this particular case, they differ at input I. And therefore, essentially the same proof works out as before. But as you can see that I will need something much stronger in order to absorb the effect of this exponential number of hybrids. Particularly, I would need I/O to be sub-exponential, and I would need the output distribution to be more indistinguishable than the inverse of the number of inputs. Okay? With that, the proof goes through. And that's why with sub-exponential I/O, we will get XPIO. All right, so the next thing is, well, okay, fine, but this seems a very restrictive notion. 2 minutes only? Oh, gosh. I think I can finish that, yeah. All right, so, but didn't I start a little bit late? All right, so we have this nice dream that, how about, what if I can, it would be nice that if I can take any CPA encryption scheme and just transform it in a generic way into a FHE, right? Then I wouldn't need to learn lattices, I wouldn't need to do any of that. And the hope is that maybe with the very powerful tool of PIO, I can do that. It turns out that we're just a little bit short from that goal, that we need the CPA to have some additional property which is randomizable. And as a natural progression, we're going to first achieve leveled homomorphic encryption and then go from there to FHE. So the second step from LHE to FHE is actually an independent transformation. And here we just need to we can work with any LHE with a fixed decryption depth. In other words, I can actually turn any of those LWE-based LHE scheme into a fully homomorphic encryption scheme, assuming slightly superpolynomial secure I/O without any circular security assumption. Okay, so and I think that this is of independent interest. Fortunately, since Amit only gave me 3 minutes, so we're not going to go over that in this talk. All right, so just the first part. And the construction is, again, extremely natural. What am I going to do with the LHE? Just like all constructions, I'm going to attempt to enable homomorphic evaluation layer by layer. Right? To do so, I'm going to associate with each layer a pair of keys. And if I look at a NAND gate at a certain layer, the homomorphic evaluation is going to derive the ciphertext of the wire values under the public key at the layer I-1, and we'll attempt to try to get the ciphertext of the output wire under the public key of the next layer. Okay? Well, the most natural idea to enable this step is I'm just going to obfuscate a program that takes in two ciphertexts. He's going to decrypt it using the secret key for that layer, and then compute the NAND and re-encrypt. Okay? So that's like, everybody would like this paradigm to work out because that's really natural. So now think about what the adversary. So what the adversary is going to get in the end, or you can think about what the system is going to release in the end, is going to release the public keys, and then the adversary at some point is going to get an encryption of some random bit B, and he, as a part of system, is going to get a list of evaluation keys, one per layer. Okay? And I want to argue that the secret bit B is hidden. Okay? What else can I do that? I have to rely on the CPA-Security of the public key scheme itself. But except I can't really immediately do that because those evaluation keys contains lots of secret keys inside. Okay, so I cannot really rely on the semantic security of the PK0, for example.
Only evaluation key 1 kind of contains decryption key, right?
Right, evaluation key 1 contains that. Right. So in some sense, I want to eliminate the secret key in evaluation key 1, but in order to do that, I will end up needing to eliminate all secret keys in order evaluation key. Okay? So let's start with trying to do this process of eliminating the secret key from the last layer. Okay? Let's look at the last layer evaluation key. It does what? It does decryption, compute, and encrypt, right? And how about I just, instead of fastgating that, I'm going to fastgate in this toy circuit, which does nothing except from just encrypt 0 and output that. And the idea is that, well, because actually the secret key for the last public key appears nowhere. Okay? Because after the last layer, I don't need to further homomorphically evaluate, therefore I don't need to decrypt the last layer public key. The secret key appears nowhere, therefore the output of those two circuits are actually indistinguishable. Therefore, by PIO, their fastgation should also be indistinguishable. Oh, great. Once I have done that, in some sense, I've turned the second last evaluation key to the last evaluation key because the secret key doesn't appear anywhere. Therefore, I can just do this hybrid and, backwards switch in all the evaluation keys one by one. I eliminate all the secret keys inside. Now, ta-da, this ciphertext is hiding. Okay? Great. Except that there's a problem. The problem is that the fact that this PIO only work with X-indistinguishable distributions comes into the way that it will make the size of those evaluation keys blow up. Why? Because if I look at one intermediate evaluation key, to argue that in order to apply PIO, I will actually need their output distribution to be very, very, very indistinguishable. How? It's negligible over the number of inputs. Therefore, it means that for each of the evaluation key, I will need the size of the output ciphertext to be way bigger than the input ciphertext. Because that's necessary. If that's the case, well, too bad. If I just start with evaluation key 1, the ciphertext blow up a little bit, the output ciphertext blow up a little bit, which becomes the input for the next evaluation key. It blow up even more, and then it grows exponentially.
There's only a constant number you need.
Maybe additively?
Oh, the number of evaluation key depends on the depth of your circuit.
But if the increase is just additive, you're saying it has to be multiplicative?
It's multiplicative, right? Because to get 1 over X indistinguishability gap, you actually need the size of the encryption to be poly. Yeah. All right. That's why we don't achieve the dream, and we need something a little bit more, which is, I'm going to actually start with using what we call this kind of perfect lossy public key. So this kind of public key encryption has two modes of the public keys. One is a normal mode, which is like any CPA encryption scheme. The other is the trapdoor mode, which actually has perfect hiding property and no correctness requirement at all. Okay? It's because that it doesn't have any correctness requirement, that's why perfect hiding is possible. And note that I cannot work with just any lossy public key encryption scheme. I actually need it to be perfect. The hiding property is perfect. It isn't enough to be statistical. Okay? And this can actually be constructed if I have re-randomizable public key encryption scheme.
Also, you can base it on two-message OT, which is perfectly secure for the sender. This is strictly more general.
I see. Okay. Thanks for letting us know. Letting me know. Okay. All right. So let's see that. Why does this help? Basically, what it helps is that instead of letting this security loss happening inside those hybrids, I'm going to make the security loss happen outside it. Even before I start switching all the evaluation keys, I'm going to switch my public key to the trapdoor mode. Once I have switched the public key into the trapdoor mode, note that all those public keys are going to be perfectly indistinguishable, no matter it's encrypting whatever value or encrypting 0. Now I can go through all those hybrids I have done before without any problem and without any size blow up.
But is the evaluation circuit still well defined? Is the NAND circuit still well defined when the
Yes.
is a lossy?
Yeah.
So there's still some secret key, so it still thinks it's decrypting things.
So you will have to, okay, I cheated a little bit. You cannot really switch the trapdoors right beforehand because there are many public keys, right? There are many public keys, one per evaluation circuit. So what you need to do is switch the public key and then do the indistinguishability step, and then switch the second public key to the indistinguishability step. So it's kind of interleaved. Not happening at the beginning.
The
Yeah.
point is 0 times exponential is still 0? That's the point? So you're saying this...
The point is that I want the output distribution to be very, very indistinguishable. If it's perfectly indistinguishable, meaning that they're identical distribution, then it satisfies my requirement.
The only way you avoid the size blob because it's 0, okay?
Right. So I don't necessarily need it to be 0. I just want to say that the gap is really small, independent of the size of the input. Yeah, it's real. Yeah. Let me leave it there. Amit is already, but thank you very much for letting me finish.